Hi, in this video, I'll continue my journey into metric spaces, where in the previous video, I've talked about functions and introduced the limit values of functions. In this video now, I'll talk about continuity. And so continuity, like the notion in calculus, but made generalized using a metric instead of absolute values, we can say that f is continuous if and only if for every epsilon, there will exist a delta such that when x is delta close to p, fx is epsilon close to fp. And so, in the definition of continuity, we need fp to be defined and fx to approach fp as x approaches p. And so what this really means is that the limit as x approaches p of fx equals to fp. So you just like subbing in the value here. And so, this p again is a limit point because it uses the same notion. But everything you know about calculus remains to hold true. And so, let's take some examples of continuous functions. And the classic one is of course the constant function. And because you can just let delta to be 1, and for every epsilon, it will hold. And since epsilon is arbitrary, the limit of x approaches c of the constant function is b. Another form of continuous function is a map into a singleton. And that's the same reason for a constant, but now a bit more generalized. And so you can see when we generalize to a metric, we want our notions in specific cases to still hold true. So they still hold true, but we're just playing around with different notations. So really, you just need to remember your specific examples and know at what point do the specific examples break down. And so again, we have a sequence criterion for continuity, and it is actually just saying the sequence criterion for convergence of functions, but now you converge to fp. So I hope it's very clear, and I'll skip the proof because it's the exact same proof as when you're doing the sequence criterion for convergence. And we can now prove that the identity map is continuous because given a function, a sequence Pn approaching P, there exists a cutoff such that for all n's larger than this cutoff, the distance between Pn and P is less than delta. And so now given epsilon, we just take delta to be epsilon. When this less than epsilon, it means that when you run it through the identity, it will still be less than epsilon, and we're done. So you can see the proof for why the identity function is continuous is the same as when we did it in the calculus video. So if you don't understand it here when we use sequences, you can check out our video in calculus where it uses the delta epsilon version. But sequences are very nice to play with, and when you have that, it really simplifies certain properties of continuity. And so when we want to prove that f is continuous, if the composite functions are continuous, we can just use the sequence criterion and we are done. So given an epsilon, we know that f is continuous and g is continuous. So because g is continuous at fp, there exists some number such that the delta, the distance between y and fp is less than n, will imply that the distance between gy and gfp is less than epsilon. And because f is continuous, we can make this true by finding a delta such that dfx, fp is less than n. And so we just need to choose this delta to fulfill this condition, which then fulfills this condition, and we're done. Again, you can also reformulate this into sequences. So this is the delta epsilon proof. For sequences, you just find a sequence of Pn's approaching P, then Fpn will approach Fp, and this G of Fpn will then approach G of Fp, and so we are also done. And so you can see how the sequence criterion is more straightforward in a way that you can calculate the value by using what we have taught in sequences. And so we can prove another thing is that when we have a metric space mapping from X to X cross X, or X to R cross R n times, or k times, then this mapping is continuous if and only if each individual function it maps to is continuous. And so the proof of the inequality follows because we can bound the vector function by each component and the sum of the components to the power of 1 over k. And so it follows from earlier when we prove the continuity in sequences, convergence in sequences. And so this thing converges if and only if, will mean this is bounded, and so it converge, and it will mean if this converges, then we can flip it around and say this part needs to be bounded as well for it to converge. And so we are done. And then with that notion that we can also prove that the addition map and so on are all continuous, and that's because of the property of the limits. So the addition map, the negation map, the multiplication map, and the division maps are all continuous. And really, you're just applying the properties of the limit to prove the following result. And because of this, we can now say that when we take two functions and add them together to form a new function, it will be continuous. And really, it's because it's a composite of mapping x to real cross real, then mapping it back to real. Because you can see x is sent to fx and gx, and this is continuous by our earlier proposition if and only if f and g are continuous, which is given to be so. And so when you use the addition map to map fg and fg plus fx plus gx, it will also be continuous because you have proven that the addition map is continuous. And so f plus g, this function, is now continuous. And you can also then show f times g is continuous and f divided by g is continuous. And so why should we care about this? It now gives us more examples about what maps are continuous, and this allows us to prove that monomials, which is basically, we already know xi is continuous, so the coordinate is like how fx1 comma fx2, this is continuous. If f is continuous, then fx1 is continuous. So now you can multiply these different functions together and form this new monomial, and then you just take the sum with scalar multiplication and it becomes a polynomial. And this really follows that polynomials are continuous by what we have proven over here. And so this example that shows polynomials are continuous should be easy to follow, so I'll leave it to you to read it. But now you are trying to understand more and more functions and what functions are continuous and what are not. And in this case, we have now proven that polynomials, which is very important when studying analysis, is continuous. And so that's all for this video. I've now talked about continuity, and in the next video we want to talk about a more general form of continuity in metric spaces. So I'll see you in the next video. Bye!